Okay, so does anybody have any specific ones you want me to go over on that big assignment on gravity? Talk to me, Carson.
6.
6?
Yeah.
Okay. So here's story number 6. So here's your nucleus. Here's this electron moving around like this. So when you look at the history of the structure of the universe, okay, and how we thought it was. So in the early or mid 1800s, John Dalton, if you remember your Chem 1, John Dalton was the first one to come up with an atomic theory, okay? And one of the things he says that atoms are combined in whole number ratios, which is why water is H2O and not H3O1/8, okay? And the main thing that's relevant to this, he said that atoms are indivisible. So in other words, in his mind, atoms were these tiny, tiny bits of matter that could not be further subdivided. So the word atom actually comes from the word atomist, which was the Greek term, which means indivisible. So John Dalton he had studied the history of this, and how the universe existed goes all the way back to the Greek philosophers, 400 or 500 BC. Okay, so this isn't like a new debate. This has been going on for quite a while. And so up until about the 1920s, roughly, everybody thought atoms were indivisible. You could not find smaller and smaller particles. J.J. Thomson was a physicist, and he was the first one to find the first subatomic particle, and he found the electron. Okay, cool. So now they knew there were negatively charged particles. They said, okay, well, cool. Well, if there's negatively charged particles, there has to be positively charged particles because the universe is basically neutral. Okay. Well, then they said, well, how does the structure exist? They said, well, they had the plum pudding model. They still stick with the idea that the atom is like a tiny bit of matter. And the negative and positively charged particles are evenly embedded within it because it's stable. Oh, that's a good idea. So then, Ernest Rutherford comes along. He's also a physicist. And he says, oh, let's shoot things at the gold foil. Okay, cool. We'll shoot things at the gold foil. Alpha particles, it turns out that was a helium nucleus. And most of the particles went straight through, and every once in a while they would bounce back. So Rutherford comes along and says, whoa, rewrite the books again. And the publishers said, would you all figure out the structure of the universe? Because we're always having to revise these books. So now all the guys that were doing this work were physicists. Okay, they were all physicists, and they'd all studied gravity like you all are doing right now. So once they figured there was a nucleus, they said, oh, we're just going to think of the atom as being like a shrunk down solar system. So instead of having the sun and Earth orbiting around the sun, we're going to have the nucleus and the electrons going around it. So it's a shrunk down version of the solar system. Cool, okay? And that fit with their mindset, okay? Oh, right. We're just going to take the idea of a solar system, we're going to shrink it down. Instead of having the sun, it's going to be the nucleus, and instead of having planets, we're going to have electrons. Cool, works. Okay, so then they started doing the math, and the math turns into an absolute train wreck. So well, maybe it's gravity that's holding the electrons in orbit, just like gravity holds the Earth in orbit around the sun. So on this first one, I've given you the mass of the electron. It's a tiny, 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 tiny bit. Proton is actually about 1,800 times greater. That's 10 to the negative 27th. And you have the distance, which is how far apart they are, which is a tiny, 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 tiny bit. So you want to determine the gravitational force of attraction between them. So on 6A, you're just going to plug them into your basic idea that F equals big G, mass of the electron, mass of the proton, divided by distance squared. Okay, you don't have to solve anything. Okay? All you do is just plug the numbers in. Okay? Now, that answer should be an incredibly small number of like 10 to the negative 47th. Okay? So that first answer on 6A should be 10 to the negative 47th. It's a very, 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 very small amount of force. okay? It's an incredibly small amount of force. So then on B, they said, okay, the electrostatic force, because they're oppositely charged particles over that same distance, is 8.2 times 10 to the negative 8. Still small, but compared to the 10 to the negative 47, it's a lot bigger. So to get your answer to 8B, just take that electrostatic force, 10 to the negative 8th, and divide that by your answer to number for letter A. Okay, because the electrostatic force is a lot bigger because that's 10 to the negative 8th. The gravitational force is 10 to the negative 47. So your answer to 6B should be like about 10 to the 40th. Okay, it's an ish, but it's about 10 to the 40th times greater. So what that means is that the gravitational force compared to the electrostatic force, that electrostatic force over the same distance is 10 to the 40th times greater. So here's this is what they figured out. If gravity was as strong as the electrostatic force is, we would not be here having this discussion because you could have had the Big Bang, but if gravity was that strong, the universe would have went boop, boom, and just would have collapsed right back on itself because there would have been such a strong gravitational field that the universe couldn't have expanded. It would have tried and then just boom, right back in. Okay. So then what I want you to do on 6C is that, okay, well, what if we wanted that electrostatic force to be the same as the gravitational force? What mass of proton would we need? So basically what you want to do on 6C, go to this, go F equals big G, mass of the proton, mass of the electron, divided by distance squared. So what you're going to do is you're going to substitute in here that 10 to the negative 8th. Okay, so you're going to know you're going to know that number. You're going to know the distance. You're going to know big G. You're going to know the mass of the electron, and then you're going to solve for the mass of the proton. Now, let me give you all a hint. You are not in Algebra 1 anymore. Get over it. Do not go through, and this is something that Carson alluded to earlier. Solve this equation first. Don't write in all of these numbers and then try and solve it. Don't write the mass of an electron 3 times trying to solve a variable. Get this thing by itself algebraically. Multiply by d squared, go, oh, fd squared divided by big G, mass of the electron, boom, there's the mass of the proton. That is so much easier than rewriting all these numbers 4 times, okay? Just work with the variables. Then, even with the big G, you don't need to rewrite big G's time. By the way, this is mass of an electron, not the mass of the Earth. Do not look at that and go, oh, that's the mass of the Earth. No, that's the mass of the electron. So what you should see on 6C, if you do that right, the mass of the proton should be like 10 to the 12th kilograms, which would be about 10 million times greater than the mass of your car, okay? So if you want gravity to hold an electron in orbit around the nucleus, each proton would be about 10 million times the mass of your car. So that's why the electrostatic force is cool, because it does that work. I mean, gravity is there, but it's just basically, it's such a small amount, it really doesn't matter. Okay. Anyway, so that's kind of a cool one. On number 5, that should be 10 to the 16th. And that, on that question, that obviously changes because of the fact that Uranus and Neptune are always in orbit. That distance is continuously changing. But that's just kind of a snapshot. It's like, okay, hey, what's going to be that gravitational force there? On number 16, that's just old school kinematic equations. So your answer to 16 should be around 4-ish. Okay, that's an ish, but it's around 4. And your answer to 16B would make a not so good GPA. And again, you're just going old school, use that equation on both questions on number 16. Now, when you get to 18, 19, and 20. So, if you look at 18, 19, and 20, there's a couple of ways you can visualize this. One is like a gravitational well. So imagine that I have this tennis ball, which I do, and I throw this ball up in the air, and it goes a certain distance and comes back down, right? So imagine I'm at here on this Earth's gravitational well. So here's the mass of the Earth. It's creating this deep curvature of space and time. So if I basically throw the ball up, it's going to go a certain distance up, and then it's going to come back down. If I throw it faster, it's going to go farther away before it comes back down. So the faster I throw this thing, the farther it's going to go, but then it's always going to come back down. But if I reach what's called this escape velocity, then if I throw it, then it's going to leave the gravitational field of the Earth, and it's not going to come back. Okay? So imagine I'm throwing it fast enough where it goes outside of that gravitational well and doesn't roll back. Okay? So obviously that's going to be really fast, because the Earth is a really deep gravitational field. So you all have a certain escape velocity because you all have mass. Okay? You all work space and time. So, when you write your college application, what's your superpower? I work space and time. Okay? We all do. Get over it. It's like you're not the only one that does that. Anything that has mass works space and time. So conveniently, you all don't have much of an escape velocity. It isn't like, Devin throws his pencil, and then all of a sudden the pencil comes right back to him because he didn't throw the pencil fast enough to get rid of his escape velocity. Okay? The escape velocity is an incredibly small number. But on Earth, it's big. So here's what I want you to see. First off, it's a different equation. There's a 2 in there, which is going to be big G, mass of the Earth over R. Okay? So that's how you're going to calculate that escape velocity. So like on number 18, that escape velocity should be something times 10 to the third. Okay? Now, when you get to, and you've got to go back and you've got to look at find the mass of the moon and find the radius of the moon. Okay? So then when you get to number 19, the whole key to number 19 is that you're talking about leaving not the gravitational field of Mars or the Earth or something like that. You're talking about leaving the gravitational well created by the sun. Okay? So if you look at this equation, you would plug in if you actually wanted to calculate it, you would plug in the mass of the sun, and then you would plug in how far you are from the sun. Okay? So when you look at that, obviously the farther you are from the sun, the bigger that radius is going to be. If you divide by a bigger and bigger number, your escape velocity becomes less and less and less. So this has nothing to do, your answer to number 19 has nothing to do with the mass of Mars versus the mass of Earth. Okay, that isn't the equation. The equation is the mass of the sun and how far you are from the sun. Okay, the mass of the planet doesn't matter. You're talking about leaving the gravitational well created by the sun. When you get to this idea of black holes, which are pretty cool, it's the whole idea of black holes. And so basically, if you look at this escape velocity, imagine that you had such a deep gravitational well that even if you shot something out at the speed of light, it still couldn't escape. Okay, and so that's kind of the short version of black holes. Like we think there's this massive black hole in the center of the Milky Way galaxy. Okay, in any galaxy we think there's a big massive black hole. And you get into what's known as event horizon, and weird things happen when you get to black holes. Time slows down because it's such a large mass. There's some weird things happen. So, but the idea being is that you can't escape. And so when you look at black holes and talk about masses, typically you express the mass of a black hole in terms of what's called solar masses. So like a typical black hole, we think might have a mass of like 5 solar masses. So in other words, imagine that the mass of our sun, and the mass of our sun is like contains about 99% of all of the mass in our Milky, or in our solar system. 99% of the mass is basically in the sun. Yeah, Earth is important, don't get us wrong. We kind of like Earth, but relative to the mass of the sun, it's nothing. It's a very, very small amount. And even if you look at, kind of give you a cosmic scale, if here's the Earth and here's the moon, you could stack every planet in that gap between the Earth and the moon. Mars, Jupiter, Saturn. You could stack all of our planets side by side in that gap between the Earth and the moon. So if you get like some solar masses, we think might be like 150 solar masses. So it's a black hole would literally be 150 times the mass of our sun. And so it's such a deep gravitational well that you can't escape it. Yes, ma'am?
What's a wormhole?
Wormhole is basically, here's kind of a visual. Imagine that you have 2 very deep gravitational wells, okay? So a wormhole would be a shortcut between the 2 gravitational wells. So instead of going out and up like this, you would go straight across like that. So that's one idea of like space-time travel. So one analogy, it's kind of a cool analogy. Imagine that this is like, you want to get between 2 points on a flat space, so you'd have to travel across like this. But if you could warp it, space and time, and bring it together like that, then you're shrinking that distance that you have to travel. So, but the problem is, if you want to warp space and time, it takes a lot of mass to do. But that's the short version of the wormhole. It's just a burrowing in between these 2 deep gravitational wells. That's why it's called a wormhole. It's like a wormwood.
Yeah, okay.
Got it? Okay. So your answer to number 20, the mass would be 10 to the 35th. Pretty big number. Okay, anything else that you really need me to go over?
7.
So here's the story. You got little g equals big G, mass of Mars over r squared. You know everything except for the mass of Mars. You just solve for that. And then you're going to take that number and then you're going to divide it by the mass of the Earth. So what you should see is that Earth, this is a ballpark. Earth is about 10 times more massive than Mars is. Ballpark answer. Okay? Both of your answers on number 10 should be 10 to the 8th. And make sure there's 3 things that you need to answer on number 10. You need to find L1, which is obviously less than the distance to the moon. You need to find L2, which is greater than the distance to the moon. And then you need to answer that third part. It says, once it crosses L1, what's going to happen to its velocity? And then I say, explain in terms of direction of the net gravitational force. Okay? So let me give you all a hint. When any teacher says, hey, explain in terms of the direction of the net gravitational force, what do you think you want to talk about? The net gravitational force. Okay? So if you read your answer to number 10, and if you haven't mentioned something about the net gravitational force, you probably need to mention that. Okay? When teachers say, explain it in terms of this, that's the magic code. Explain it in terms of that value. Okay? All right, anything else? Going once, going twice? So if you want to hold on to this and hand it in tomorrow, that's cool. If you're done and you want to hand it in, whatever works for you. And if you're not sure if your answers are right, if you want to come up when I give you time to work, if you want me to look over what you have done, I'll look over the answers you have and I'll tell you if any of them need to be corrected. Okay? All right, so let's talk about the test tomorrow. So there's going to be 2 distinctive parts to the test. They're related, but they're like 2 sides of the same coin. So the first half of the test, and literally, these are not going to cross over, okay, in terms of like the test itself. So the first part of the test is going to be the centripetal motion part, okay? The test is about 4 or 5 pages long. The centripetal motion part will be like the first kind of 2 pages. So let's start with this very, 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 very basic idea. So I get this rubber stopper swinging around like this, okay? Here's the first question. Is it accelerating?
Yes.
Yes. How do you know?
It's not flying off into space.
Right. It is traveling in a circle. Does Mother Nature want things to travel in a circle? No, because if she did and I let go of it, what would it do? It would continue to travel in a circle. If Mother Nature likes circles, okay, if Mother Nature likes circles, then Mother Nature, when I could let go of it and then it would continue to travel in a circle. Okay, if that's what Mother Nature was, if that was the easiest for Mother Nature to do. If Mother Nature says, oh man, circles are cool, right? I like circles. Then she takes a drag on her hookah pipe. But she doesn't. Okay? Mother Nature likes straight lines. Mother Nature wants a constant velocity, which means it's going to travel in a straight line, and it's not going to change. And I know that because if I stop the force and I watch what happens, it goes flying off. Okay? And it travels in a straight line. So here's the first thing. So you've got this rubber stopper, and it's traveling around in a circle. So number one, I know that it's accelerating because I'm changing the direction of that vector, okay? Now, what's the direction of that force?
Inward.
Inward. Always inward. I promise you, okay? I promise you. Here's the first question that's going to be on the test. It's going to be multiple choice. I'm going to talk about the direction of the acceleration and the direction of the force. What were you going to look for? Inward. Okay? Inward. At a right angle to the velocity vector. Okay? I'm not going to trick you and say, oh no, it's actually going to act outward. No, no, no. It's always inward. Centripetal means inward seeking. It's from the Greek word meaning inward seeking. So that centripetal force and that centripetal acceleration are acting inward at right angles to the velocity vector. Okay? Boom. There you go. Okay? That's it. Promise you. Okay? It's not outward. Nothing. Now, but here's the problem. People think there's what we call centrifugal force. Centrifugal force means outward seeking. So here's the problem. If you're the rubber stopper, okay, and I won't do this, but because I like Bailey, but let's say that I take Bailey and I start to swing her around over the top of my head and then I let go of her. Okay, which I won't do because I like you. But so I'm going to swing her around over my head and I said, Bailey, what do you feel? She's going, oh, Burkham. Oh, I feel like I was being pushed to the outside. Okay? That's what the sensation is. Like, oh, I'm being pushed to the outside. If you're Bailey being swung around on the end of the string. Okay? Now, what's happening, and again, I'm not discounting what Bailey's feeling. Okay? She's going to feel that way. Because it's just because she has mass. She wants to move in a straight line. So what she's feeling is the action-reaction of her body wanting to move in a straight line, but there's this force acting inward. It's the same idea. Imagine that when I actually thought of all of you when I was flying back from D.C. So I was in the plane, seated there, boom, we're ready to take off. Plane's at rest. You hear the pilot rev up the engine. Okay, let's go to the brakes. Boom, plane begins to accelerate forward. Okay, and I'm sitting there and I feel like, I'm being pushed back in my seat. So is there a magic force in front of me pushing me back in my seat? No. Okay, there's not. My body has mass. My body wants to remain at rest. So what's happening is that chair is pushing me forward, and I feel that action-reaction of me wanting to stay at rest, and that force, and the force from the chair pushing me forward. Same thing is happening with Bailey. Bailey says, I'm being pushed to the outside. No, there's no magic force inside pushing you out. You just want to go in a straight line, and you feel the action-reaction of that force. Okay. So, when you talk about how you can calculate that centripetal acceleration, okay, there is a pen that doesn't write. So you can either use 4 pi squared r over t squared, or you can use v squared over r, depending upon the situation. Okay? There you go. Now, you also need to realize that if you have something moving in a circle, so let's say, for example, I've got, just dropped 1/4, I have to do another one. I'll use pennies. Okay, so I got a couple pennies. So these pennies are going around on the green spinny thing. Are they both accelerating? Because they're both moving in a circle, right? So since they're accelerating, so as those pennies go around, what do they have in common? What's the same for both pennies as it goes around? Radius? Nope. How about time? Time's going to stay the same, because both pennies take the same amount of time to go around. So what that means, if you look at 4 pi squared r over t squared, the outside penny has a bigger radius. That's going to undergo a greater centripetal acceleration. Now, you can also look at this in terms of v equals 2 pi r over t. They're both going to share the same value of time. And don't flip out and go, oh, Mr. Burkamp, that's a tough equation. It's the circumference divided by time. It's distance divided by time. That's all it is. Oh, I'm traveling in a circle. Oh, that's easy. So clearly, since on these two, they're both the same, period. They take the same amount of time to go around. Clearly, the one with the bigger radius has the bigger velocity because it has to travel a greater distance in the same amount of time. Okay? So, no matter how you look at it, the penny on the outside, whether you plug it directly into 4 pi squared r over t squared, or you go v squared over r, the penny on the outside is going to have a greater centripetal acceleration. It's going to require more force to go around. So this is why, as I make it go faster, the penny on the outside goes flying off first, because of the fact that it exceeds the frictional value of force faster than the inside one does. Now, let's talk about the forces that are acting on said penny. So, here's the green spinny thing. Here's this penny. There's 3 forces that are acting on this penny as it goes around. There are 3 forces. Jaden, what's one of them? Gravity. Okay, right. That's going to be acting straight down. Boom, there you go. That's one of them. Bailey, what's another one?
On the spinning thing?
Yes, well, it's on the spinny thing going around like this. Now, which direction is that going to act? So I've got the centripetal force acting inward. Okay, there's the third one.
Friction.
Well, that's what's creating the centripetal force. That's the third one. Rhymes with Wormhole.
Force normal.
Force normal. Okay, cool. Right? So those are the 3 forces that I have acting on this thing. Right? And they don't add up to equal to 0, and that's why it's accelerating, because they don't add up to equal to 0. Now, here's what's not here. There is not a force pushing the penny to the outside. Okay, that's not there. There is no force pushing the penny to the outside. Does the penny want to move in a straight line? Yes, but that is not a force. There is no force pushing the penny to the outside. Okay, it's not there. It's not there. Now, Emmeline brought up this idea of friction. So when you look at the 4 fundamental forces, gravity, electrostatic, strong nuclear, weak nuclear, notice that centripetal force is not one of them. Remember, centripetal force in and of itself does not exist. It only exists because there's friction, because there's gravity, because there's a string, okay? Something else has to be there to create that centripetal force. So centripetal force in and of itself is only existing because something else is there, okay? So, when you look at mu, which is equaling force friction over force normal, if you look at the basic definition of the coefficient of friction, old school, from the very first day we started to study forces, boom, this is what we got. Force friction over force normal. Now, in this situation, what's creating the centripetal force is friction. So you can go, oh, okay, right. That's centripetal force. Now, because I'm on a flat surface, which we are, the normal force is balancing out the gravitational force. Oh, I can put that as Fg. Now, if you want to get clever, you could go, oh, that's mass times my centripetal acceleration. That's mg, the masses cancel out. So you can look at this on a flat surface. Listen to me very carefully. On a flat surface, mu is going to be the ratio of your centripetal acceleration to your gravitational acceleration. Okay? So typically your car tires have a maximum coefficient of friction of about 1. Okay? So what that means, your car, when you travel around in a circle, about the maximum centripetal acceleration you can generate with your car tires is about 9.8 meters per second squared. If you try and get more than that, you're going to spin out. Okay? And that's assuming that you're on a flat surface. Now, if you look at racetracks are like slanted up, okay? And so are turns on highways. And they do that because then you're having the normal force created by that surface help you make that turn. But if you're on a pure flat surface, whether it's a coin, whether it's a car, doesn't make any difference. If you're on a pure flat surface, what's creating the centripetal force is your frictional force. Okay? Cool with that. Now, in contrast to that, you're going to have Bubba in a barrel. Okay? And I swear to you, this is exactly how this is going to be a story. I'm going to tell you. Bubba is riding in a swirling ride. Okay? It is going to say Bubba. Okay? Literally, it is going to be talking about Bubba. So Bubba is going around in a circle like this. So imagine that we're going to stopper. So I've got my rubber stopper like this. Okay. Now what I'm going to do is I'm going to swing this thing around, and so I'm going to be up like this. Okay. Now if I just let go of this rubber stopper, what's it going to do? It's going to fall, right? Because there's gravity and there's nothing else holding that up. But if I go fast enough, trying to do this without taking out anything, this will be a bonus, okay? So if I go fast enough, that stays up. But if I slow down, then it begins to fall. So if I'm going fast enough, it stays. If I slow down, gravity wins. So if that was Bubba, okay, so well, here's the platform as it goes around, same idea. Okay? So here's Bubba, right? So Bubba's going around like this, right? So there's 3 forces that are acting on Bubba. What are the 3 forces that are acting on Bubba? What's one of them? Centripetal force. Oh, that's going to be acting inward. How do I know that there was a centripetal force acting on Bubba? Because what is Bubba not doing? Bubba is not turning into a projectile. Oh, right. Bubba. Centripetal force acting. Got it. Okay, good. So, Bubba's going, here, hold my moon pie. I want to go on the ride. So, you got the centripetal force, right? We're also in a gravitational field, so what else is acting on Bubba? Gravity. Okay, gravity. Now, if those were the only 2 forces acting on Bubba, what would Bubba do? Bubba would fall down, okay, because there would be nothing to balance out gravity. So that means, what else is there? There has to be an upward force that balances out the gravitational force acting downward, right? And so that's going to be friction between the surface and Bubba, okay? So at a minimum, that frictional force acting upward has to balance out the gravitational force acting down on Bubba, okay? That's what has to happen. Now, basically what happens is this. You can use an analogy of your hands. If you rub your hands together and your hands are barely touching, okay, there isn't very much friction, right? Because they're just barely touching. The harder you push them, the more friction that there is, okay? Same thing happens with Bubba. So what happens is as Bubba goes faster and faster and faster, what's happening is that there's more and more centripetal force. So that's like pushing Bubba between that surface and Bubba that's pushing harder and harder and harder. So it's like your hands, there's more and more friction as you push harder and harder and harder. So here's the story. Now here's the difference. Mu is still going to equal force friction over force normal. Okay, it's the exact same idea. You cannot deviate from the basic equation of mu. Now here's the difference versus this on a flat surface versus Bubba going around in a circle. Here's the fundamental difference. In this one, the force friction is balancing out the gravitational force. So the force friction is acting up, and that's balancing out the frictional force, which is acting down. Now, the normal force, remember, always acts at right angles to the surface. So as this thing is going around, that centripetal force is acting inward at a right angle to the surface. So with Bubba's in a barrel, and I will literally, again, I'm telling you, Bubba is going to be in a barrel. That is the exact words I'm going to use. Look for Bubba in a barrel. So the normal force is what's going to create the centripetal force. So then you can go, oh, that's mg, that's mass times centripetal acceleration. You get a ratio of g over ac. So these are inverses of each other. So if Bubba's driving his car on a flat dirt track in Georgia, then in that situation, you have AC over G. But if Bubba goes, man, I'm going to take Darlene to the carnival, it's in town. We're going to go ride the ride when the floor drops out. If that's the case, then it's going to be G over AC. Now, here's the story. Let's talk about Bubba. So imagine this is the wall. You're like this, right? Okay? And Bubba gets off the ride. And we go, Bubba. I'm a reporter from the local newspaper. I go, Bubba, what happened? Bubba's going, oh, it was intense, man. It was intense. I said, what happened? I said, man, I was being pushed up against the wall. I felt like I was being abducted by aliens. I was being pushed against the wall. I said, really? He goes, yeah, man, I couldn't lift my head. It was an intense experience. Cool. Now, was Bubba being pushed against the wall? Or pushed? However you want to say it.
No.
No. Imagine I could make this room spin, which would be cool. And you're all like this up against the wall, right? And you all are going to feel like you're being pushed, right? But is there some magical force that exists inside this room pushing you against the barrel wall? No. What does your body want to do? Move in a straight line. Okay? So all that's happening is that action-reaction. I promise you, I'm going to ask you this question, and I'm going to expect you to be able to articulate this idea. It's one of the most important things. And it's going to be about Bubba. I'm going to say, Bubba claims he was being pushed up against the barrel wall. Is Bubba correct? Okay? That's the question. I promise you that's going to be the question. And you just need to say, no, Bubba, 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 Bubba. You just wanted to go in a straight line. The wall was preventing you from doing that, and you felt that action-reaction force. Okay? That's what you want to be able to do. Okay. Now, here's the other type of problem you're going to deal with. So, my problem right now is I've lost my rubber stopper. There it is. Okay. Now, rubber stopper. Speaking of gravity, now I want to make it go around in a loop like this. Okay? So now I've got a vertical loop. So we're going to deal with two extremes. We're going to deal with what's happening at the top and what's happening at the bottom. So, if this is this rubber string, whoop. So you got this at the top, and you've got this at the bottom. When is the string going to be most likely to break, top or bottom? Bottom, why?
Because force of gravity is acting with centripetal force.
Close.
And that force is greatest.
There you go. So here's the story. So if this is just here like this, no movement at all, just have this, okay? You just have this. How much upward force is acting on the string? Enough to balance out what? Gravity, right? Whatever the mass in stock is, we take mass times 9.8 meters per second squared, boom, that's the force going down. String is balancing that out. Now, when this thing gets to the bottom of the swing, does it want to travel in a circle? No, what does it want to do?
Stop.
Wants to turn into a projectile, right? So at the bottom of the string, that string has to do two things. It has to overcome the gravity mafia, which is trying to pull it down, and it has to provide the centripetal force to make it move in a circle. So at the bottom, you're going to add these things together. So you're going to have Fc plus Fg equals your force total. Now, remember, that total force is what you are going to experience. So like right now, you all are experiencing Fg. Okay, that's it. You are always experiencing Fg. And again, imagine that I could take this room and I could rock it back and forth like a big swing set. Okay? So when you're at the bottom, it's like, whoa, we're going to feel heavy. Because not only is gravity trying to pull you down, and the chair has to balance that out, push you up so the gravity doesn't pull you down, you also have to have the force to make you travel in a circle. So this is why you're always going to feel heavy at the bottom. Now, up at the top, okay, up at the top. So if we add at the bottom, we're going to subtract at the top. Oh, force total at the top is going to be force centripetal minus Fg. Now, you have to look at what you have on your equation sheets, okay? You don't have either one of these equations on your equation sheet. Okay, they're not there. They are not there. They're individually there. Oh, here's the equation for centripetal force. Oh, here's the equation for gravity, okay? But you just have to remember, oh, right, at the top, it takes a certain amount of centripetal force to make this thing move in a circle. But gravity now is helping you out. Gravity is providing a lot of that force, okay? So this is why up at the top, if I'm not going fast enough, I don't complete that loop. But if I am going fast enough, then that string stays tight. So as I slow down, if I slow down too much, it doesn't complete that loop. So there's a couple of things at the top that you need to be able to do. There's a couple of things you need to be able to do at the top. So let's focus on that. So first off, realize that force total is Fc minus Fg. So at a minimum, to complete the loop, you want to be like in a state of weightlessness. So if you want to calculate the minimum velocity that it takes to complete a loop, you're going to be in a state of weightlessness. So in other words, gravity is providing just the right amount of force to keep you moving in a circle, otherwise known as being in orbit. So you'd set that equal to 0. You have Fc minus Fg. Move that over there. So here's the basic idea, is that your centripetal force is what's created by the gravitational force. The two values are equal. We've seen this before. Okay, it plays out in circular motion as well, even with satellites. It's the same idea. So then you go, oh, well, that's just going to be mg. Oh, that's going to be mv squared over r. So oddly enough, your mass is going to cancel out. Oh, cool. So you get v equals the square root of GR. So what that tells you is the minimum velocity that it takes to complete a circle. Now, if you want to put something in orbit around the Earth, guess what? You're going to use 9.8 meters per second squared in the radius of the Earth. And that's going to tell you how fast something has to be going on a large scale to be in orbit around the Earth. If I want to do something simple with this cup of water and swing it around, okay? So if I want this thing to go around and me stay dry, I can calculate that minimum velocity, and then anything above and beyond that is just gravy, okay? So v equals the square root of GR. That's just the minimum velocity that you have to have. Now, I promise you, you're going to have a roller coaster problem. It's going to be at the bottom of the front page, okay? We'll tell you exactly where the problem's going to be. And I'm going to give you the velocity and we'll say, hey, is it going fast enough to complete the loop? So one option is that you calculate the minimum velocity using this equation, and if that velocity is bigger than that, you're going to complete the loop. That's an option. Okay, that's one option that you can do, calculate the minimum velocity. The other thing that you can do is say, oh, okay, right. If you're going to complete the circle, your total force needs to be a positive number. So if you take the difference between the centripetal force and the gravitational force at the top, when you subtract those values out, if that's a positive number, you're going to complete the loop. That's an option. You can also look at this in terms of going, oh, that's mass times v squared over r minus mg. So if you take v squared over r and you get that acceleration, and that centripetal acceleration is bigger than 9.8 meters per second squared, you're going to complete the loop. So when you get to this question, it's going to be the last problem on the front page. I'll tell you exactly where it's going to be. When you get to that problem, and I ask you, is it going fast enough? And that's what I'm going to ask you. You can say, you can calculate the minimum velocity. Oh, that's faster than that. It's going to complete the loop. You can calculate your centripetal acceleration using v squared over r. If that's bigger than 9.8 meters per second squared, you're going to complete the loop. There's any number of ways you can work this problem, okay? I don't care. Just find one that you're comfortable with. Now, it was the last centripetal motion assignment that I gave you all, okay? It's on a purple sheet of paper. There are problems like that. Again, make sure that you know how to do those problems. Go back, look at the very first question on that assignment was a mass being swung around on the end of the string, okay? That problem is going to be the very bottom problem on the test, on the front page. The only difference is that I'm going to use a roller coaster. That's it. Now, here's the other thing that you need to be able to do, is that when you look at force total equaling force centripetal minus Fg, when you're at the top, this can be a multiple of your gravitational force. So let's say you're at the top and you want to feel 1/4 of what you normally do. So what you can do is come over here and say, okay, if you want to feel 1/4 of what you normally do, you would say, oh, that's 1/4. Come on. Oh, I hate my pen. 1/4 Fg equals Fc minus Fg. Okay? So then you're going to move this over here, and you're going to get 5 force mg equaling mv squared over r. Oddly enough, your mass is going to cancel out, and you would have 5 force grr, and the square root of that is going to get you that velocity. That's how it's going to play out. This is going to be the top problem on the second page of the test. Okay? Here's the only thing I can do. The only thing I'm going to do is change that fraction. It might be a half, it might be 3/4, it might be an eighth, it might be a 1/6. Okay? So on that assignment, you all did, let me see your assignment. Inland. Okay? So down here on this question number 4, okay, the vertical acceleration, etc. It's going to be a question like number 4. And notice on here you have like 1/4, a half, 3/4. Literally, it's going to be a question like number 4. The only thing I'm going to do is, the only thing I can change is what fraction of your weight do I pick. Do I pick 1/3? Do I pick 3/4? Do I pick 7/8? Okay? Whatever that is, that's the fraction. So literally, the only thing that you can change is that fraction. Okay? Cool with that. Top question, second page. That's going to be right before the Bubba in the barrel problem. Okay? That's what it's going to be. I'll tell you that right now. Okay. So, Kepler's laws. Gravity. So, when you get done with that, then I'm going to tell you, oh, hey, here's going to be the next portion of the test. This is going to be the gravity portion of the test. So, you're going to have a question involving Kepler's laws, TA squared over TB squared equals RA cubed over RB cubed. Okay? On this problem, and it's going to be like 2 moons orbiting a planet. That's how this problem is going to play out. It doesn't make any difference in this one what units period is in. It doesn't make any difference what units radius is in. It's a ratio. okay? So I'll probably give you this orbital period in like hours or days, something like that. So if you're just using Kepler's third law, you don't have to convert them into seconds, okay? Because it's a ratio. So I promise there's going to be a question like this. The very first assignment you all did, it was like a collection of Kepler's laws. It was a one-sided assignment, okay? Go back, make sure that you're familiar with that. So both of these, here's the only requirement, is that both of these objects have to orbit the same center. That way the mass of what's at the center of the orbit cancels out. So you could compare two moons of Jupiter. You could compare two moons of Saturn, okay? Because they're both orbiting the same center. You can compare the Earth and Mars because they're both orbiting the Sun, okay? It's a ratio, just a ratio. Don't forget the square, don't forget the cubes. Okay. Then you've got, in terms of gravity, big G, M1, M2 over D squared. Okay? So, big idea. Here's Jaden. Mass of Jaden is 50 kilograms. Okay? And if we wanted to calculate the gravitational attraction of Jaden and the Earth, I could come in here and I could plug in the mass of Jaden, I could plug in the mass of the Earth, I could plug in the radius of the Earth, and I could calculate that value. Okay? So that's one option. Okay? I could do that. I could plug in these numbers, and I'm going to get a number. And it's going to be the exact same number as if I said, oh, F equals mg, and I take the mass of Jaden and multiply that by 9.8 meters per second squared. So weight is a measure of your gravitational field. So on Earth, Jaden is going to weigh 490 newtons. Now, if we take her to Mars, gravitational field on Mars is a lot less. Is Jaden's mass going to change when we take Jaden to Mars? No, it's still going to be 50 kilograms. But instead of using the mass of the Earth, I would use the mass of Mars. I would use the radius of Mars, and I would get a different number, okay? Do not confuse mass and weight. Mass never changes, weight does, depending upon your gravitational field. Okay, so out of this, you get different equations. Little g equals big G, mass of the Earth, for example, over r squared. Now here's the significance of this. When I drop something, whether it's this little plastic marble, whoop, that dropped a long way, or a tennis ball, or Jaden, or whatever it is, the only thing that determines that gravitational acceleration is the mass of the Earth and how far you are from the Earth, okay? The mass of what is being dropped doesn't matter. It's not part of the equation. This is why Jaden, me, everything accelerates at the same rate, because it doesn't matter. What matters is the mass of the object that you're falling towards. It also depends upon how far you are from the center of the Earth. If I'm on the top of Mount Everest, little g is a little bit smaller. Okay? If I'm at sea level, g is going to be a little bit bigger. Okay? So little g changes depending upon where you are. We also came up with like V equals big G mass of the Earth over radius, the square root of that. We also had 4 pi squared r cubed over big G mass of the Earth. Now, here's the story. I'm going to pick one of these three. Either the calculation of little g, the calculation of velocity, or the calculation of period. And I'm going to expect you to be able to do dimensional analysis and prove that you get out of this little g that you get meters per second squared. Or out of v, you're going to get velocity, or out of t, you're going to get seconds. I'm going to pick one of those three. It's going to be on the second page of the test, okay? So if you want to make sure that you can do these and get them right, do these again and again and again. Make a flashcard. We're making like take an index card. Get 3 index cards. Write those 3 equations on one side of that index card. On the other side of it, do the dimensional analysis so you know how to do these problems. Okay? It's going to be one of these three. Don't get the test go, man, Burkamp didn't say anything about having to do dimensional analysis. God, what a jerk. Okay? No, I'm telling you, it's going to be one of these three. That's it. Now, here's the most critical substitution that you have to do, and it's common to all three of these. So let's say, for example, you want to do this one with period, okay, just to get it started. So you would go, okay, that's 4 pi squared. I've got a radius, which is going to be in meters, and that's going to get cubed, okay? And then I've got big G, which is newtons meters squared over kilograms squared. And then I'm going to have the mass of the Earth, which is kilograms. Now, you don't have to memorize the units for G. Look on the front of your equation sheet. There's this value for big G, 6.67 times 10 to the negative 11, and the units are right there, okay? You don't have to memorize the units for G. It's right there, okay? Now, here's what's going to happen. I'm going to cancel out the meters squared. I'm going to cancel out one of the kilograms. I don't worry about the 4 pi squared because that has no units. So that's going to be meters over newtons over kilograms. So out of the first round of cancellations, this is what I have. Okay, this is what I have left over. Now, for newtons, Tyler, what am I going to put in for newtons? What's another way to express newtons? Let me give you a hint. Mass times acceleration. It starts with kilograms. Tyler, you're making this horribly difficult.
Wait.
You're making this horribly difficult. What's another way to express newtons instead of newtons?
Kilograms meter per second.
There you go. Thank you very much. I was about to have a heart attack. Okay. It's like, have I taught you all nothing? So I got kilograms meters per second squared. So that's the single most important substitution that you have to put into this equation. It is the single most important substitution. Kilograms meters per second squared. Now, that's still divided by kilograms. Now, this is where the magic happens. Oh, those meters cancel out. Those kilograms cancel out. I have 1 over second squared, which is the same as taking the square root of second squared, which is seconds. Okay, there you go. So, honest to God, take 3 index cards. Write one of those equations on each one. On the back side of it, do that dimensional analysis. There you go. Okay? So on all of these equations, where is the radius measured from? Center out. It's never the surface distance. It's from the center out because we treat everything as being a point mass. If you're using anything involving big G, what units does period have to be in?
MKS.
Seconds. It's the MKS system. That period has to be in seconds. Guess what? I'm not going to give you the units in seconds. I'm going to give them to you in hours, days, something like that. Okay? And if you don't pay attention to that, it's going to be a train wreck. Okay? And you all sit here today and go, Mr. Burkamp, don't be silly. We'll convert it into seconds, we promise. And it's like, okay, whatever.
We'll convert it. We'll forget the radius.
I'm just telling you. Okay. So here's the type of problem that you're going to have to be able to do. And there's a problem like this on the review. I might say, okay, here's the Earth. Here's the satellite. Okay. And I might say that it takes, 20 hours to go around in its orbital period. And I might say, okay, what's the centripetal acceleration at that altitude? And the only thing you know is period. But you're orbiting the Earth. So this is about as complicated as it gets because you kind of have to work this as a multi-step problem. So first off, let's talk about that centripetal acceleration. Remember that centripetal acceleration is the same thing as your gravitational acceleration. Okay, it's the same thing, because centripetal force is created by gravitational force. So let's just think this through before you do any calculations at all. If that obviously is a long way away, because like near Earth orbit of like the International Space Station is about 90 minutes, about an hour and a half. So this thing is taking 20 hours to go around. So obviously this thing is a long way away from the Earth. Okay, it's a long way out because it has such a long orbital period. So at that altitude, what do you know about the value of little g? Is it going to be bigger or smaller than 9.8 meters per second squared? Smaller. So right away when you calculate, if you get little g, and if you get g bigger than 9.8 meters per second squared, you have done something horribly wrong. Okay? Because it can't be bigger than that. Okay, it has to be less than that. So if you know orbital period, you can go, oh, 4 pi squared r cubed equals big G mass of the Earth t squared. You know the orbital period. You know the mass of the Earth. You can find that value of r. You can figure, oh, here's the orbital radius. Now, your orbital radius, oddly enough, has to be bigger than the radius of the Earth. Okay? Because if it wasn't bigger than the radius of the Earth, it would be orbiting inside the Earth. That'd be weird. Where's the satellite inside the Earth? Really? Oh, let's think that through. That really doesn't make much sense. So you know when you find this radius, it has to be bigger than the radius of the Earth. Oh, okay, right, because you're a long way from that. Now, once you get r, and you have to find r, I swear, you have to find r. Then once you get r, then you can go, well, you could use centripetal acceleration equals 4 pi squared r over t squared. You could take that r, put that in there. You know how long it takes, 20 hours. Change that into seconds. Boom, there you go. So that's an option. Okay, cool. If you go, oh, but Mr. Burkamp, oh, man, I like little g. Cool. Little g. You could go little g equals big G mass of the Earth over r squared. Take the radius, put that in there. You're going to get the same answer because your centripetal acceleration is the same as your gravitational acceleration. Oh, okay, you can do it that way. Then you go, oh, Mr. Burkamp, I like to calculate velocity. Good. You could find 2 pi r over t. You could figure out the orbital velocity of that satellite. You could do that. And then you could go, oh, centripetal acceleration equals v squared over r. And then you could put that in there. I don't care. I could care less, okay, which method that you choose. You're going to get the same answer. If it were me, personally, I'd do that one, or I'd find little g, just because the math is easier, okay? If you held a gun to my head and said, pick one, I'd do that, because that has the fewest variables to plug into a calculator. I just have to have big G, the mass of the Earth, divided by that radius that I just found, squared, boom, that's going to be about as easy. And oddly enough, wait for it, on your review, there's a problem like this, okay? I'm going to tell you straight up, the last question on the test is going to be a problem like this. It will be the last question on the test. I'll even tell you where it's going to be. That's where it's going to happen, okay? All right, I am done. So what's going to happen with the review, you're going to have two distinct parts of the review, just like the test. You're going to have the centripetal motion part, and then you're going to have the gravitational part to it. So stop that, let me hand that out, and then we'll talk. Okay, so let me go over one problem that's on the bottom of the centripetal motion review. It has a roller coaster, and I give you like the angle and the distance, and that's old school in terms of inclined planes and calculating acceleration. On the test, I gave that just to kind of keep that fresh in your mind. On the test, I will go directly to just to giving you the velocity, okay? So I'll tell you, oh, it's going at a certain speed. I'm on the test itself, I'm not going to expect you to be able to do accelerations down inclined planes. I will just tell you, oh, the roller coaster is moving at 20 meters per second. So if you want to jump directly to that portion of the test, because I give you that number, you can. if you want to go, oh man, I got to be able to do that for the final, and you want to go ahead and keep those calculations fresh in your mind, you can do that. But on the test itself, I'm not going to expect you to do that. Now, here's the other thing that I want you to keep in mind. So, the relationship between period and frequency, if I gave you something is moving like at 45 RPM, okay, remember that's frequency, that's revolutions per minute. Remember that period and frequency are inverses of each other. So one of the things you need to be able to do is take 45 revolutions, divide that by 60 seconds and get revolutions per second. That's frequency. If you want period, you got to take the inverse of that number. So I promise you, front page, you're going to have questions about 2 quarters sitting on a spinning turntable. I promise you, and there's questions like this on the review. You're going to have 2 quarters. And they're going to be quarters, not half dollars, not pennies. They're going to be quarters. And I'm going to tell you, they're moving at a certain number of revolutions per minute. This is what you've got to be able to do. And like I said, there's a question like that on that review. Okay, I'm done. You're on your own. Tomorrow we'll rock and